Good morning, everybody. Please take a seat. And this morning we have the first talk is a keynote lecture on operational systems and application. And the speaker is the Director General of ECMWF. She has been leading ECMWF since January 2016, and her career has been sort of back and forth between ECMWF and Meteo France. She contributed to the setup of Ordivar, the operational system which has been running for several years now at ECMWF. And it is a pleasure for me to introduce Florence Rabier for the speaker of this morning.
Okay, thank you very much, Jean-Pierre. Good morning, everybody. So it's my pleasure to start this morning's session with this historic view of ensemble prediction at ECMWF. So in autumn 1992, that's when we implemented for the first time ensemble prediction. So this is actually 25 years, and we are celebrating this autumn then. So first of all, sorry, I went the other way around. For some of you who might not know us, what is ECMWF? It's European Centre for Medium Range Weather Forecasts. It's an intergovernmental organization supported by 34 member incorporated states over Europe, and this is our print over the European continent. And so we have more than 300 staff, and they are coming from 30 different countries. But of course, we play a unique role in Europe because we are this intergovernmental organization doing global numerical weather prediction. But we also have a global collaborations with many organizations around the world, and in particular, actually 25 years ago, it's also when ensemble prediction was implemented at ENSEP in Washington. And at the time, and people might remember that, we really had a lot of collaboration with ENSEP, who were using different methods for ensemble prediction. But so this is going to be our story at ECMWF, but obviously we were not the only ones thinking about ensemble prediction, and in the last 25 years, much more has happened in the field. So basically, if you want to summarize what is ensemble prediction, basically instead of running one forecast, we run 52 forecasts now. And this happened then in 1992. How were you set up? How were we set up? In 1992, we had one model, the model and the forecast. It was high resolution at the time, 100-kilometer grid space, and it was starting from so it was one atmospheric model starting from one initial condition going up to 10 days, doing a 10-day prediction. So it was pretty simple, really, although it was quite complex, the equations and or everything that went into it. The setup was actually quite simple compared to what it is now. So in 2017, where are we? We still have this high-resolution model. It's not 100-kilometer grid size anymore. It's 9-kilometer now. So we've made quite a lot of progress in 25 years. But it's also starting from one initial conditions, but we also have an ensemble of initial conditions, an ensemble of data simulation, and we have an ensemble forecast, 51 member. That's why I say we are going to 52 forecasts now, because we have this high resolution and 51 members of an ensemble forecast. It's not just the atmosphere, it's also coupled with a wave, and actually the ensemble is coupled with the wave, with the ocean, with the sea ice. We also have an ensemble system, an ensemble analysis of ocean, and we also extend this to the seasonal scale. So much more complicated, and I will go through what led us there. So sometimes it's a bit complicated to explain ensemble prediction. We did a few graphics for those of you who might not be so familiar. So basically, we start with a description of the atmosphere, but we don't just do one description of the atmosphere. We do several variants of it. So we have 50 different initial conditions, which will then lead to 50 ensemble members. And that's how it started, 50 different initial conditions. And I have another small illustration. So from these 50 ensemble members, then we run 50 times the model. And in the end, we have a forecast, and in every grid point, then we can have probabilities of what's going to happen based on these 50 different forecasts. So how are we doing in ensemble prediction? So measuring the performance of ensemble prediction is a tiny bit more complicated than measuring the performance of the deterministic forecasts. But still we do it, and we've been doing it for years. And we've also looked at the progress in the last 25 years. Here I represent the progress in the last 15 years. And so this is what we measure usually is the continuous ranked probability score. And basically, when it's going up, it's better because it's the time range at which this score reaches a certain value. So in weather forecast, in global weather forecast, we usually say that we improve by 1 day per decade. So typically the performance 15 years ago, that was five days. We would have it at 6.5 days. But actually, in ensemble prediction, one can see that we're actually progressing faster than the deterministic forecast. For this particular score, which is 850 hectopascal temperature, it's more 2.5 days in 1.5 decades, so 1.7 day per decade or something like that. So it's following the track, you know, it's following the progress of the model itself, but also of initial conditions and also how we actually build the ensemble system. And we can say that we had some steady progress in the last 15 years. What's important in ensemble prediction, what it gives you, it gives you a range of scenarios where the atmosphere could go, and it also gives you a spread of the forecasts. So when you run your ensemble members, if they are very close together, then you can have a really good confidence in your forecasts, which if you just run one forecast, you have no idea whether this particular one is good or not. But if all your ensemble members are close together, then you can think, well, actually, there's not too much uncertainty in the atmosphere and we can trust the forecast. If they start going in all directions and the spread increases, then that's when you think, well, actually, maybe the forecast is not so good or we can trust it beyond a certain number of days. So what's important is to have a sort of coincidence between the spread of your ensemble forecast and the skill of our forecast. What we would like to do is being on this diagonal here, that when you have a larger spread in your forecast, you know in advance that on average this forecast will not be as good as if you had a smaller spread. So this is what it shows here for different time ranges. It's all about the northern hemisphere for the geopotential 500. This is 1 day forecast, 2 days, 6 days, and 10 days. So we can just, for instance, look at this 6-day forecast, which is well into the medium range in the northern hemisphere. So what we would like to do is be along the diagonal. And as you can see, ECMWF here in red is pretty much along the diagonal. So we are actually doing not too bad a job as being informative in advance about the quality of our forecast, which is what you want from an ensemble prediction. So typically, if we have a smaller spread in the ensemble, so it looks more condensed, then yes, it does correspond to actually a smaller error than on average. So it's not perfect, but you can see that actually we are not too bad. Usually ensemble systems tend to be under-dispersive and they underestimate actually, the spread underestimates the quality. At day 10, we also are a bit under-dispersive. So I think that's quite good to look at more detailed measures like that of what it can bring ensemble prediction rather than just one given score. So this spread-skill relationship is really what a forecaster would like. So when you see the forecast and you look at the spread, you immediately know this is going to be probably a good or a bad forecast. So I could trust it or not in doing my analysis. So we started with just the atmosphere up to 15 days, but now it's not just that, and we've extended so in the last 25 years. So we're going towards a more Earth system approach, where it's not just the atmosphere, but it's all the coupling with all the corresponding parts of the envelope of the Earth. So we have coupling with the ocean, we have coupling with the sea ice, we have coupling with the land, and we are extending that to our ensemble prediction system. This coupling with different components, in particular with the ocean, allows us to push the limit of predictability of our system, and in particular, going to extended range and seasonal range, and we do that with the ensemble system. So what is the extended range? Basically, twice a week, we run not only up to 15 days, but up to 46 days in the ensemble, in the extended range, so more than a week ahead. So then we start off looking at anomalies for week 2, week 3, week 4, and this is indicative of large weather patterns over Europe, for instance. So how did it improve our extended range forecast? So we didn't start that immediately, but we started that in the mid-2000s. And as you can see, the scores are not so regular, but there is a bit of a steady increase as well at week 3 and week 4. It might not be as large as for the ensemble prediction. So this is more tricky. This used to be called the desert of predictability. It's really quite tricky to do extended range forecasts, and you really need to have everything right to get it right. But we are steadily improving, and we are always trying to do the best in our model, in the coupling, in trying to see where the sources of predictability are in order to improve this extended range prediction. I said it's not just the atmosphere, it's also the waves. We've been coupling with the waves for a long time, and we also can compute scores for our ensemble prediction of waves. So we have waves coupled to all our systems from the beginning, and this is again some scores in the wave ensemble forecasts. So this is just to show how it expanded since 1992. Also, we are now part of the Copernicus Emergency Service, and we are contributing to ensemble forecast of floods over Europe and also globally. This is the EFAS and GLOFAS system. EFAS is European Flood Awareness System, and GLOFAS Global Flood Awareness System. In that system, we put some ensemble members and produce ensemble forecasts of flood. We don't just use the ECMWF, we also use DWD forecast in order to have a more global ensemble of the floods in Europe. Okay, so that then gives you the breadth. So how did we improve? What were the major changes in the last 25 years at ECMWF to improve the ensemble forecasts? Where we started from is using what we call singular vectors. So these are the modes of the atmosphere that are going to be the fastest growing in the first few days. So it's not the long-term growing modes. It's really the ones that are going to really explode in the forecast and gives us the maximum spread in the forecast. So this is what we've been doing from the beginning. Ensemble prediction was using singular vectors. And this was a bit different from what the Americans were doing at the time, where they were doing bread vectors. They were not computing it similarly, but they were also trying to find the most rapidly sort of growing modes of the atmosphere. That was the very beginning of ensemble prediction. That led to under-dispersive ensembles. Then, of course, it's not just the fast-growing mode in the forecast. If you want to be a bit more realistic about what really happens, you have to realize that our physics parameterizations are not perfect, and maybe we can tune a bit that or perturb that a bit to show the uncertainty we have in physical parameterizations. So in 1998, we started to include some stochastic physics, which are perturbations of the physics in the model. And this shows that the ensemble is more reliable. This is a difference between the scores with and without. And actually, the CRPS goes down, which is good, which is including stochastic physics actually improved the ensemble prediction. So ever since 1998, we have been also perturbing the physics going forward in the model. Also, what we've been doing, I told you already about monthly forecast extended range. So we've been merging the ensemble with the monthly range and actually using the coupling with the ocean. So this is just an example showing that the extended range is much better if you couple with the ocean rather than if you have persisted SST. In particular, then after the medium range, you really need coupling with the ocean rather than just persisting the sea surface temperature. So coupling with the ocean was important, especially in the extended range, but we also applied that to the medium range. And then another step, which we did in 2008, is actually being a bit more physical about, this fast-growing mode. They didn't have any link with what we were doing in data simulation, for instance. Or we know that there are some errors in the observations. They are not perfect. They have some random errors associated with them. We also know that our data simulation is not perfect. So then, at this point, we try to show the uncertainty in the data simulation process itself, which leads to uncertainty in the forecasts. So we started running this ensemble of data simulation, which is sort of extended the ensemble prediction backwards and running an ensemble of data simulation showing the uncertainty in the data simulation itself. So this is what we've been doing. Then it's a bit more consistent, an ensemble of data simulation and an ensemble of forecasts. So then we added some perturbations defined by this ensemble of data simulation to the ensemble so that it was sensitive to these small errors or perturbations in the ensemble conditions. It was not the only purpose of the ensemble of data simulation, which is also a way of quantifying the statistics used in the data simulation in 4D VAR. So it shows us the statistics of the background error, of the model error in the short range. But it was in particular used from 2008 for the ensemble prediction. What we've done very recently, in November 2016, is actually coupling the ensemble. It had been coupled with the ocean since 2013, but then we increased the resolution of the ocean model to 1/4 of a degree and 75 levels in the vertical. This is our NEMO model we use in the forecast. And also we have introduced interactive sea ice. So it's another step towards Earth system modeling, coupling with the land, of course, we were doing from the beginning, with the ocean since 2013. And since 2016, we've also been coupling with the sea ice. These plots show the reduction in the error in the sea ice concentration at day 10 when we have this sea ice interactive in the ensemble. So it gives us some spread in the sea ice and some better forecasts. So that's basically where we are now after all these developments, starting from singular vectors and then stochastic physics, ensemble of data simulation and more coupling, and pushing to the extended range and of course the seasonal range. So what sort of products do we provide then to the forecasters? This is one of the products we put on our website now. So it's the high resolution forecast. This is for surface pressure. But superimpose, you have actually the spread of the ensemble. So it tells you one picture, but it tells you also where you have the larger spread from the ensemble. So it gives you immediately one picture of what happens for a given field over the globe. Then, of course, if you want to go to one precise point, so this is for instance, Reading, United Kingdom, where ECMWF is located. We have these ensemblegrams where we show these box and whiskers diagram, which shows you the variability in different parameters for a given point for the forecast. So it shows you that at the beginning, there's not so much uncertainty, for instance, here in the temperature, max and min temperature. Then it grows a bit, but it gives you a trend then later on for whether it will be above average or below average, for instance. We also do clusters because the whole point of ensemble forecast is not just to give an error bar. That could be done statistically. We wouldn't need to maybe to be so sophisticated if we just wanted to give an error bar on the forecast. What we want to give is also really the range of possible scenarios of the atmosphere in the coming days and weeks. And actually, when we look at the 51 members, they're all different, but you can group them, and some of them are more similar than others. And the clustering does that. They actually group all the 51 members into different categories where they actually look very similar, and we can relate them to some of the large-scale climatological regimes which we know over Europe, Atlantic. The blocking, the positive NAO, negative NAO, etc., and Atlantic ridge. So then the forecasters can have an idea of how many members are predicting a ridge and how many member positive NAO, etc. So it gives already some idea of the weather regimes in the long range. Something which is one of our top sellers in terms of hits, or people really look at it because it's a very good way of condensing information, is this extreme forecast index, which on a map actually manages to compress the information of all the ensembles, of all the cumulative distribution function of one parameter. So this was, for instance, for wind gusts. This is when a storm was coming across Western Europe. And the EFI tells you how much the actual distribution of members in the ensemble, in the current ensemble, is different from the climatological one. So, for instance, here, if this is the climatological distribution of 10-meter wind gusts at a given point there, and these are the forecasts, you can see from the beginning, from the medium range, oh, it seems that it's going to be more windy, and it's becoming more and more straight, which means less and less uncertainty, and you can say that there will be quite surely a 30 knot wind gust for the 10 meter. So this is actually very, this is a lot of information, but you can condense that into one number saying how different these distributions are, and this is what is plotted here. So the brighter the color, the more abnormal the distribution is, so more different from the climatology. So this gives you very, very quickly a sort of idea of what's going to happen, if it's going to be sort of normal or not. Now, I couldn't resist, when I talk about ensemble prediction, I love the tropical cyclones example just because it's very visual and it's very, we all know that tropical cyclones can have some devastating effects, so a lot of people look at our tracks of tropical cyclone. When I prepared this talk, we were in the middle of tropical cyclone Harvey. If I had done it yesterday, I might have shown a tropical cyclone Irma. As you know, we have these very dangerous tropical cyclones coming over the US. Harvey has done a lot of damage, and Irma is on its way to Cuba and maybe Florida. So, I mean, we will see what it does. But this is for tropical cyclone Harvey. The sort of representation sometimes we have is this probability that Harvey will pass within a certain radius within the next 10 days. So this was the forecast from the 21st. This is the high resolution in the solid line. We have the ensemble mean in the dashed, and then you have all these colors that really shows the probability, so it condensed the information of all the 50 ensemble members. So as you can see from the 21st, we were already predicting the sort of strange movement that Harvey had, which it came onto Texas and then it stalled there before going back to sea and going up again. So the exact location was not absolutely right, but there was an indication of this behavior of tropical cyclone Harvey. And this is then, we produce that in the medium range. In the extended range, we also do then probabilities. So this is strike probability, and this was actually from the 14th of August, the strike probability of a hurricane, and we can see here that there was something in the Gulf there. So this is very tropical cyclone ensemble products. Definitely, if you just, actually we were lucky there that the high resolution was very good. I mean, I wouldn't say we were lucky, it's because it's a good forecast, but you know, sometimes it varies from one run to the next, etc. Definitely when it comes to tropical cyclone in the medium range, it would be absolutely absurd to just look at the high resolution forecast. You definitely need to look at all the ensemble members because there's usually quite a large spread after a few days. And that gives you much more information than just the high resolution forecasts. So this is a range of product we are producing at the moment. Where are we going from there? So this is a summary slide of what our strategy looks like. So we have a new strategy for 2016-2025. So we will continue to focus on high-impact weather, and some of the maps I've shown, like the EFI, tropical cyclone, etc., really concentrate on high-impact weather. Regime transition in the longer range, this is absolutely important in Europe. Our member states are quite adamant that they want to know in advance when there will be a change in weather regimes, when it's blocked and when it will stop being blocked, etc. And then global scale anomalies, we want to predict the El Niño with as many months ahead as possible. We will continue to develop an Earth system model and analysis. As you can see, we've made a lot of progress in Earth system modeling. Next implementation, we will actually implement the coupling of the high resolution with the ocean as well. So we will have this consistent model of coupled with the land, with the ocean, with the sea ice for both the high res and the ensemble. The analysis, we made some good research on trying to have a coupled data simulation with the ocean, and we've done some research in reanalysis mode, and we would like to extend that to the operational daily runs. We want an integrated ensemble at 5 kilometers by 2025. This is quite ambitious, but this is the direction we want to look at. We don't want to look at separately at the high-res and the ensemble anymore. We really want to look at integrated products between the ensemble members and possibly some at higher resolution, but not just looking at the high-res. We really want to put the focus on the ensemble, which is more than an add-on to the high resolution. So there's really a shift of focus from the high resolution to the ensemble in the next 10 years. But we realize that resolution is very important, and we would like to have high resolution ensemble. All this is not affordable if we don't make a special effort to fit our code on the next supercomputers, and we are spending quite a lot of time and effort in trying to be innovative in the way we can fit all these computations to be as efficient as possible on the future supercomputer. And of course, we are devoting also quite a lot of our time at ECMWF to work on environmental information services, and this is the Copernicus service. I just mentioned the EFAS previously, which is our contribution to the emergency management service, but you had a session yesterday about the climate change service. Ensemble prediction at ECMWF extends also to an ensemble system of reanalysis. The reanalysis is going to be an ensemble as well. And also, of course, we are doing ensemble seasonal forecast at ECMWF for our model, and Copernicus within ECMWF is also doing this multi-model ensemble for seasonal prediction. So all this is also very much linked to ensemble forecasting and analysis. So how can we keep improving the ensemble? Well, a bit of everything. Obviously, we can't have a good ensemble if we don't have a good model, and we always want to improve the model, and we're working hard on all the aspects, the dynamics, but of course the physical parameterization. But we also need to work on quantifying better model uncertainty. So not just the model, but model uncertainty. How can we quantify that better? Initial conditions, so at the moment we only have 25 members for the ensemble of data simulation and 50 members of ensemble prediction, so we don't have a one-to-one correspondence. We want to work on maybe making it more seamless. Ideally, we would like the same number of ensembles in the data simulation and in the forecast. Ensemble methods, as you see, there have been different ways of improving ensemble method. We want to continue to improve how we do it, so we want to look at different compromises between resolution, membership, and how the length of the forecast, etc., of the reforecast to do some relevant products. And predictability, there's also some longer-term research which is about looking at the sources of predictability. For instance, did we neglect the stratosphere? And if we want to have a relevant ensemble in week 3, week 4, we actually really need to have better simulation of the stratosphere and how it interacts with the troposphere. Is it in the snow, the evolution of the snow, that we can find more predictability as well? So there's a whole range of scientific research which can then trigger us to work in different directions for the ensemble model. So that's basically where I wanted to take us. So this is very short. It's not, it's very high level. For those of you who know what ensemble prediction is, it's a bit of the B.A.B., as we say in France, B.A.B.A. So it's really the first steps of understanding ensemble predictions. I just wanted to give you an overall view. Now, next week, starting on Monday, we have this seminar at ECMWF, which is dedicated to ensemble prediction. And of course, I just presented it at ECMWF, ensemble prediction at ECMWF. This was the scope of this talk, to show what we've done. We haven't done this alone, of course. We are embedded in the European context. We are collaborating a lot with our European colleagues. As I said, we started this development as well with a close collaboration with NCEP in Washington and with the US. So, of course, plenty of things have happened, and in collaboration with us or independently. And in the seminar, we'll try to cover that, and there will be a lot of interesting talk from many people. This will be live streamed, so if you can't attend, you can go on our website and look at the address, and you can see which sort of presentations there are there, and attend as many talks as you like. So this will be much more getting into the heart of the matter and really giving you more details about everything that has been going on, not only on global models, but regional models, etc., and not only over Europe and at ECMWF, but really much more broadly. So with that, I will finish my talk. Thank you very much.